So our speaker today is Daniel Roggenkamp from Leipzig. Will tell us about Rozansky-Witten models as extended defects TQFT.
Yes, thank you very much for the invitation to this great workshop. So what I want to do in this talk is I want to explain how to construct arbitrary correlation functions in Rozansky-Witten models. And for this, I will use a very explicit construction of the respective extended topological quantum field theories using defects and then employ the cobordism hypothesis. So that's kind of the basic idea behind this. And Rozansky-Witten models is just a very specific kind of a 3D TQFT. For me, this 3D TQFT is more like a toy model or example. So one should use this kind of construction, which I want to explain here, in a more broader context. And I think it should be applicable to most other theories as well, once you have a good handle on the defects of these theories. This is sort of the whole talk goes back to project together with Ilka, which is also here, Niels Karkvil and Pantelis Frakos. Okay, so since this talk should be somehow accessible to a broader audience, I decided to skip over loads of technical details. So I'm sorry about this, but I will be here the entire week. So if anyone wants to know anything about the technical details, then I'm happy to talk about this after the talk. Okay, so now I start using the Blackboard, but maybe if I do it like this, I don't have to switch off the projector. It's a no, okay, then I will.
Just turn on the light.
Oh, turn on the light. Okay, this was this one. Was it this one?
On and off for 2 things.
Ah, okay. Okay, so one, so TQFT as a functor. So I'll start with the functorial approach to topological quantum field theories, and this goes, of course, back to Atiyah and Siegel, or at least it's attributed to them. So a d-dimensional TQFT is supposed to be a functor, let's call it capital T, which goes from a Bordism category, let's say board N, where N is the dimension of the TQFT, or let's say D, if it's d-dimensional TQFT, to the category of vector spaces. So the category of vector spaces everyone knows. So what's this category? Well, the objects in this category are closed and compact d-1 dimensional manifolds, and the morphisms between them are Bordisms. And here I should say that this is not only a functor, but this is supposed to be symmetric monoidal functor. So what does this mean? So monoidal basically means that both of these categories have a monoidal structure. Here, that's just the tensor product structure, and the monoidal structure is basically something which generalizes the notion of this tensor product. And in this category, this is just the disjoint union. So that's somehow the definition, if you would like, of a d-dimensional TQFT. I don't want to go too much into the technical details or the abstract definitions, so I'll just give you an example to show you how this works. So let's start with the 2-dimensional TQFT. So what is this category here, board 2? And now I have to switch off this. So the objects in board 2 are closed, compact, 1-dimensional manifolds, so basically disjoint unions of circles. So these are the objects here. The morphisms are Bordisms between this. So in this case here, for instance, there's a Bordism between 3 disjoint circles and 2 disjoint circles. So I read this from bottom to top. That's morphism between these things. And of course, in this category, you can compose morphisms. And the composition is just gluing along these boundary circles. So for instance, if I have morphism like this and one like this, then I can compose them by just gluing this thing to the bottom of this thing. Okay, that's how this category works. And okay, and now I go back to this blackboard. So TQFT, 2D TQFT, is now a functor which associates to a circle some vector space V, because that's what it's supposed to be, right? It's a functor. It's monoidal. That means it respects the monoidal structure. So if you have some disjoint unions here, let's say you have M circles here, then this has to be mapped to V, the M-fold tensor product of V with itself. And finally, if you have some Bordism, let's say, some topological surface like this, well, this has to be mapped to some phi in Hom of V tensor 3 to tensor 2, so some linear map like this. So that's what the TQFT, 2D TQFT does. And functoriality tells you that, well, if I glue something to the bottom of here and I then take the image on the right, then it's the same as just composing linear maps, which is a very easy thing to do. Now, board 2, this category here, is very special in that it is generated by a finite number of generators with relations. It's a very nice presentation. So finite number of generators. And these generators are the cap and the pair of pans and the handle. So every sort of morphism here can be glued together out of these three very simple pieces. And there are some relations which they have to satisfy. So I give you one example. So if you, for instance, do something like this and glue two pair of pans like this, then you get well, a surface which looks like this. And this, of course, you can also get this by somehow pinching off a pair of pans on the left. So that's the same as this one. Okay, so that's one relation, that these two things have to be the same. Okay, so by means of functoriality, so I now, okay, maybe I use a second blackboard now. Okay, by means of functoriality, you can now basically, you have somehow two nice things, or this gives you two nice things, this presentation. So one is computability. Because once you know what your functor does to these three pieces, you can basically calculate everything. So TQFT is determined by T of these generators. Okay, so once you know all these, then it's very easy to compute everything. So for instance, the correlation function of a torus can be calculated by somehow cutting up the torus into these pieces. So that's just T of this cap and composed with T of the pair of pans, right, composed with T of this handle. Okay, so just have to compose these three linear maps which you have to get this, and using this you can get all the correlation functions. But that was one thing. But the other thing which is remarkable is that by means of this sort of generators and relations, you also get a classifications to classification, and that's a famous result which states that 2D TQFTs are basically in one-to-one correspondence with symmetric Frobenius algebras. Okay, so the somehow T of the circle is the Frobenius algebra over there, and T of pair of pens is just the product, and T of the cap is the trace in this Frobenius algebra, and T of the handle, well, I won't write down everything, but the point is that all these relations are basically in one-to-one correspondence to the conditions for this thing A to be a symmetric Frobenius algebra. So in this case, in this 2D case, things are quite nice, but the problem is that this doesn't hold for higher dimensions. So in higher dimensions, the Bordism categories aren't that nice, so they aren't that simple. Let's put it this way: there's no prescription in terms of finite numbers of generators and relations, so you can forget about this program. But fortunately, there's a way out, and this goes under the name of extended TQFT. So it's one uses a kind of more local structure. Okay, so that's number 2. Extended TQFT. Okay, and that goes back to Bayes, Dolan, and Lurie, and Fried. It's invented in the 90s, I guess, 1990s. So the idea is to replace in the setup before the category board by a higher category board n minus 1 up to 0. And this is a higher category which somehow encodes more of the local structure. So first of all, maybe just a reminder what higher category mean. I'm not sure if everyone knows what this means. Should I do this? No? Yeah? Okay. Okay. So, right. So in an ordinary category, you have objects and also morphisms. So between two objects, there's a set of morphisms, which I write like this. Is there a pointer also? Not sure. So like this. So F, for instance, is a morphism between A and B. And the point is that you can compose morphisms. So if you have two morphisms, F from A to B and G from B to C, then you can sort of stick them together. Ah, okay, thank you. Stick them together like this to get a new morphism. So think about the category of sets and maps, for instance. So that's an ordinary category. Don't worry. And now the idea to get higher categories is to enrich this by giving somehow these sets of morphisms the structure of a category. So now these morphisms F from A to B are now objects in some category. And with this comes the fact that there are morphisms between them. So let's say you have a morphism F from A to B, and you have a morphism G also from A to B, then there's a morphism now in this sort of higher, in this category more of AB from F to G, which one usually denotes like this in two categories. Okay, so you have sort of richer structure of morphisms. So there are now morphisms between morphisms. And these can be composed again. So if you have alpha from a morphism from F to G, let's say alpha, and you have beta from G to H, then again, as in the normal categories, you can, since this is a normal category, you can just compose them and get another morphism. And that's what is called a two composition, because these morphisms are two morphisms and one just composes them. But the point is that now these morphisms here are categories, and this one composition is somehow a map between two categories. One really wants the structure of category to be preserved by this composition maps. So these composition maps are not only maps anymore, but they are functors between categories. And since they are functors between categories, they also map morphisms to other morphisms. So this means that there's a higher, so another product or another composition between two morphisms, which is called one composition. Oh, can one read this? So let's say you have a morphism alpha between F and G, which go from A to B, and you have morphism alpha prime from F prime to G prime, which are morphisms between B and C. You can now also compose them by somehow composing these maps here. So, and that's the one composition. That's the composition on two morphisms coming from the one composition here. And this is like this. So that's another sort of more structure to it. So there are more compositions. And of course, these two categories, there are lots of additional axioms. I haven't mentioned the axioms of a traditional category, but you know, there are more and more. And now you can go even further and say, well, I mean, to get this thing, this structure, this two category, we said, well, these morphisms are just categories. But of course, we could also say, now that we know what a two category is, we can say, well, why not taking this morphisms and making it into two category? And so between, now we have somehow also morphisms between these morphisms and so on, stacks higher and higher. And you know, if I take this to be a two category, then I would get a three category, and the axioms get sort of, the rules of the game get more complicated the further we go. Okay, so that's basically what I want to say about n categories. And of course, sort of an n category is obtained by sort of, you know, taking the morphisms here to be n-1 categories. And so that's a recursive, kind of recursive definition. All right. So I said here, exactly. You know, as I said, I didn't want to go into technicality. It's technically enough, I think. So, but there are axioms. But you know, there are more axioms, because here you see in the two category sense, you know, you have to have compatibility between this one compositions and two compositions. You know, you can compose them in different ways, and this gives you somehow much more relations. So it's much harder to test if something is a two category than to test if something is just a category. Okay, so here on the board, I said that one should replace boardisms or board n by this sort of higher category. So let me just explain the higher categorical structure of board 2. So board 210. So that's the next thing. Okay. So board 210. So the objects of board 210 are now zero-dimensional manifolds. So what are zero-dimensional manifolds? They're just points. So either you have an empty set, a zero-dimensional empty set, a point, 2 points, and so on. So that are the objects of board 210. Yeah. The one morphisms are just one-dimensional boardisms between these objects. So for instance, you have one morphism between a point and one point, which is just the interval like this, or you can have a Bordism like this between 2 points going in and the empty set going out. So I read these graphs from right to left, just to make life easier. So this here would be a morphism between this object, namely 2 points, into the empty zero-dimensional set. Yeah, I go from right to left. Before I went from bottom to top, and now I run from right to left. Okay, and what is gluing? Well, composition of one morphism is just gluing. So for instance, you can take this one morphism and this one morphism. So this here goes from 2 points into empty set. This goes from empty set into 2 points. You can compose them or glue them and get the circle, which is a Bordism between the empty set and the empty set. So that's the rule of the game. As before with the 2 dimensions, you do this now sort of in 1 dimension. So it's kind of easier. But of course, you also have 2 morphisms, and the 2 morphisms are now 2-dimensional Bordisms between 1-dimensional, so between these 1 morphisms. So for instance, the cap here is a morphism between the circle on the bottom and the empty 1-dimensional set on the top. Or the saddle here is a morphism between 2 parallel intervals like this and these arcs here. Okay. So these are 2 morphisms. Is this clear? I mean, just ask questions if you know, it's kind of important. So please ask. This is fast, I know, but you know, it's supposed to be informal. So these are the 2 morphisms now in this category. And there are 2 kinds of compositions, namely, as we've seen before, there is the 2 composition and there's a 1 composition of 2 morphisms. And this is both gluing of surfaces. So once is the gluing somehow on the along horizontal 1-dimensional things like this. I glue this here, you know, to this, and that's the 2 composition, right? It's composed along 1 morphism, so that's a 2 composition. But you also have the 1 composition, which is a gluing from left to right. So for instance, you can glue this thing here to the saddle, and this would be 1 composition of 2 morphisms. So you have these 2 types of compositions here. Okay, so that's basically this board 210 and the 2 category structure of this. Now I go back to the blackboard. So an extended TQFT is now a functor T from a board n minus 1, n minus 2 up to 0 into some target category, also an n category n. And that's an n functor. That means it's compatible, preserves this n category structure, and it's also symmetric monoidal, as you know before. But don't worry too much about these details. The point is, you know, this is supposed to be a functor like this. Okay, and the nice thing about these things, so these extended TQFTs, is that this n functoriality now implies what we had before, namely computability and also classification. And this is due to the so-called cobordism hypothesis. Okay, and proved by Lurie, and I think these guys put it forward first. So, and this hypothesis says that this category board n minus 1 and so on until 0 is generated by the point which is fully dualizable. And all adjunction data. Okay, so that's the hypothesis. I want to explain what this means. So, what does it say? It says, like before in the two-dimensional TQFT, right? This is generated by something. In this case, by the point, and which has to be dualizable, and all the adjunction data. So I want to explain to you what dualizable is and what the adjunction data is. So that's the next step. Okay, so dualizability means the following. So an object V in a monoidal category is dualizable if there's another object V star, think in vector spaces, the dual vector space, and adjunction maps. So there are special maps. So there's the evaluation map, which goes from V star tensor V to C, where C here is the monoidal unit in this category, like, for instance, the ground field in the category of vector spaces. And a co-evaluation map, which starts in C and goes to V tensor V star. And these maps have to satisfy the following relation, namely, if you compose these maps, so first V goes into C tensor V, so this is the monoidal unit, so C tensor V is isomorphic to V, so there's a specific isomorphism here. Then you take the co-evaluation on C, which maps the C to V tensor V star, and then on this you take the evaluation on this part into C, and then you take again this isomorphism from V tensor C to V. Okay, so you compose all these maps, and what you have to get is the identity, right? So that's what dual vector space means, and one often uses some graphical notation. So the evaluation map sort of starts in V star tensor V and goes to the C. So you have something like this. The co-evaluation looks like this, and then you can write down this relation in this form. So where here this lambda V is this isomorphism, rho V is this isomorphism, and you can sort of take this apart like this. And then in this sort of graphical notation, it looks like you just have to somehow pull on the ends of this thing to make it straight, because this is kind of the identity here. So that's why this is sometimes called the Zorro move, this duality relation. Okay, so let's talk about duality in this boardism category, board 210. Okay, so the objects are zero-dimensional manifolds, so points. So I have to tell you what is the dual of a point. And the dual of a point in this case is just the point itself. Okay, so next I have to tell you what are the adjunction maps, this evaluation and co-evaluation map. Well, the one adjunctions, so the adjunctions of this, are this. So the evaluation is just this arc, which goes from 2 points into the empty set, which is C, so the tensor unit here. And the co-evaluation is just the arc in the opposite direction, like this. So this goes from the empty set on the right to 2 points on the left. Okay, so these are the one adjunctions, and they satisfy this Zorro identity. Why? Because now if you compose them like this, so that's kind of what this composition is, then you get this S-shaped one-dimensional manifold. But this is a topological manifold, so you can just pull it straight and get sort of the straight line, which is just the identity on the point. Okay, and you can do it in the other way. So this satisfies these kind of Zorro identities. And the important point is that these Zorro identities are really just, telling you that everything is topological. So whenever you see a kink or something, you can just pull it out and flat. Okay, but now the problem is this was a 2 category. So these things here, this evaluation and co-evaluation maps, they are objects as well in some sort of other category. So fully dualizable means that also these adjunction maps have to be dualizable, and you have to have higher adjunction maps. So what are the duals of these adjunction maps? Well, the dual of this adjunction map is just the other one, and the dual of this adjunction map is just the other one. So that's sort of the higher duality. And now I have to give you the adjunction maps, and the adjunction maps look like this. So this is the evaluation of the evaluation. So that was the evaluation, and that's the evaluation of the evaluation. It goes from the dual of the evaluation, tensor the evaluation, tensor product was just this joint union, to the identity in this category, and the identity is just sort of straight lines. So that's the identity in the respective category. And the adjunction map associated to this has to be some Bourdism, like, well, any Bourdism between this and that, but the Bourdism to choose is this one, is this kind of upside down saddle. And then you have the co-evaluation of the evaluation, which now goes from this to the circle, which is the composition of evaluation and co-evaluation. So the tensor product, which in this case is just the composition. And so you get the cup there. The evaluation of the co-evaluation is the cap, and the co-evaluation of the co-evaluation, we take the saddle. Okay, so that's just the definition of some maps which could be the duality maps. And now, of course, one has to check if they satisfy these Zorro identities to be sure that they are really dualities. And indeed, this satisfies the Zorro moves, because if you write down the Zorro moves for these kind of maps, then you get, this thing here. So you have to glue, we know what composition and so on is in this category is just gluing. And if you take all the pieces for the Zorro identity, you see that what you get is something like this. So it's the gluing of these pieces here. And if you put it together, well, it looks like this here with just a little bit of edge here. So since there's a topological surface, we can just pull at it and make it sort of straight. And the straight thing is this, which is the identity on the co-evaluation in this case here. So that was the Zorro move for the co-evaluation. You can do the other Zorro moves as well. It always looks like this. So the Zorro moves in this case also tell you that this is topological. You can pull things flat, and then everything works out. All right. So now I go back to the blackboard. So the cobordism hypothesis says basically that as in the 2D case, well, everything now is generated by the point and all these adjunction maps. So that's the point, and we have these things, and then we have the higher adjunction maps, which is this, and then I have the saddle, or the upside down saddle group, and the saddle function. Okay, so these things generate the entire category. So once you know what your TQFT does on these things, then you can calculate everything. Okay, so for instance, let's just make an example. So the torus. Oops, no, I have to turn off the light here. Okay, so if I want to see what the torus, how to formulate the torus into these pieces, I just cut it like this, and you see here that the torus can be glued out of this. These are always the identities. So if you take the interval times something, it's just the identity. So these are, I didn't write them here, but they are somehow implied. But these other parts, this, and this, are just evaluation and co-evaluation maps. So and every sort of the cobordism hypothesis tells you that every surface can be obtained in this way. So you see what this is. So that's the identity on this arc. This is the identity on this arc. This is the co-evaluation of the co-evaluation, the co-evaluation of the evaluation, evaluation of the evaluation, and evaluation of the co-evaluation. Okay, so once you know sort of the duality structure, you can do everything.
So in the case of rule 2, it's kind of complicated than the original generators, but
in board 210, you mean? Yeah, now, of course, I mean, in board 2 was kind of the simple example. I just want to tell you, I mean, want to explain to you how this extended thing works in board 210, but of course, you know, the real application come in higher dimensions. Right? No, well, finite, it's always, you know, it's always generated by the point and the higher junctions, you know. And there, you know, you start with a point, you get this, this, and this. But now, let's say in board 3210, these things are object as well. You have to find duals to these, and then the three-dimensional cobordisms, which are the evaluation there. And, you know, you have to pick them, and, you know, but this works. That's sort of the point about this cobordism hypothesis. And in this case, you get all these generators. Okay.
just with this completely explicit for all.
No. No. I mean, the cobordism hypothesis also, I think it's proven for low dimensions, but I'm not sure what the status really is. You know, I think people believe it works. But I don't know. I'm not, you know, that much of a mathematician. So. But it's supposed to hold, and it certainly works in the example I want to explain. Okay, so now the extended TQFT now. So once you know T of the point and T of the adjunctions, you can compute everything. Everything is computable as before. Okay, so that's one thing, that's number one. But number two, there's also a classification. Because somehow extended 2D TQFT is it's just a fully dualizable object in an or no 2D sort of d-dimensional, I should say extended d-dimensional TQFT is a fully dualizable object in a D category. Let's call it C. So if you know a fully dualizable object in some D category, then by means of this construction, you can build out of this, just since you know T on all these, on all these things, you can then define correlation functions on all, all boardism in this category by this. So that's the classification result. So again, sort of in this extended context, you have computability and classification results. Okay, so the problem with this, of course, as you pointed out, this gets more complicated in higher dimension, and also, all these axioms are very complicated. So, so not very many examples, explicit examples, are really known, and what I want to explain to you now is what we did together with Ilka, Niels, and Pantelis. Namely, we obtained a very explicit construction of the extended Rozansky-Witten models. So that's part 3. So these Rozansky models are twisted, so topologically twisted, 3D n equals to 4 sigma models on with target spaces, hyperkähler manifolds, hyperkähler target spaces. Okay, very specific things. And now if I tell you I want to construct sort of an extended Rozansky-Witten model, the first thing I have to give you is the target category, because that's something you have to specify. So as target category, what we do is we choose the 3 category of defects in Rozansky-Witten theories. Okay, so now I have to explain to you what I mean by this. So I go back to the slide. So, what are defects? I mean, this workshop, everyone knows what a defect is, but how do they form a higher category? So if you have an n-dimensional quantum field theory, you can get an n category of topological defects in the following way. So the objects are just n-dimensional quantum field theories. The one-morphisms are n-1 dimensional topological defects satisfying the respective quantum field theories. The two-morphisms are somehow n-2 dimensional topological defects separating n-1 dimensional topological defects and so on. So you have to have this kind of picture in mind. So this is an n-1, so this surface thing is an n-1 dimensional defect separating a quantum field theory defined on one side and one on the other, which might be different. And on this thing, which I now drew as a surface, I have lower dimensional defects. So for instance, I can draw a line here which separates two of these sort of codimension 1 defects. And this is also a defect now, which is a two-morphism. So while this was one morphism, this is a two-morphism. And then I can go on. So the point defect is then a three-morphism between different two-morphisms. So in this way, somehow that's the way I think about higher categories, is by thinking about this example, because that's very obvious. It's an obvious example of a higher category. Right? These defects, topological defects, give you a higher category structure. And of course, I have to explain what is composition, but composition in the topological context is just, if you have topological defects, you can, move them around space-time. So in particular, if you have two parallel ones, you can just put them on top of each other, and this gives you the composition. And all the compositions, all the higher compositions are this. So for instance, if you have n-morphisms, which I denoted by points now, or drew as points on the line defect. So think about this as n-morphisms, and then you can just move them together to get a new n-morphism, and that's the n-composition in this sense. But of course, you have another composition, namely if you have two of these sort of line defects next to each other with point defects inserted, you can also move these two close together. So while this was the n composition, this is the n-1 composition of the n-morphism, right? We had these different compositions in the higher categories, and these are the different compositions. So these defects are just an example or give just an example of an n category.
So you mentioned n. Should I think of that as a vector space of observables at that point, or is it a particular?
So the point defects, so if I think about sort of normal quantum field theories, then I would say at the highest level there should be vector spaces, right? Because if you have an n-dimensional quantum field theory, it should associate a Hilbert space to an n-1 dimensional manifold. So that's kind of something you can put in if you want, but the whole notion works even if you don't think about vector spaces at all. So you can forget about this actually. So you wouldn't need, but you can certainly do this. And the example we have, that's the way it works. So we have vector spaces in the places where we want from a physical perspective.
But I guess my follow-up question, and maybe it's more math question.
Yes.
Math question, not a physics question. But if the top dimension you have vector spaces, typically you would expect there to be one dimension beyond there. Like, in a category, you want to be able to say whether morphisms are equal to vector spaces. You should only say they're isomorphic.
Isomorphic, yes.
So but to be as suggested, this should be a n+1 category rather than n category.
Well, actually, so maybe somehow there's a confusion about the highest dimension. So the vector spaces are somehow, if I have an n-dimensional quantum field theory, then the vector spaces show up at dimension n-1, because that's, the n-1 dimensional spaces are the vector spaces, and the homomorphisms between them are kind of the highest dimensions, so elements. So like a correlation function, right, is a homomorphism between sort of tensor products of vector spaces. So the vector space, you're right. I mean, that's completely correct what you say. It's just that my n is different than yours. So you're completely right with this. So the vector spaces, so the isomorphisms, are in the highest sort of level. Okay. All right. So that's the n category of defects. Now I want to come back to my example here. So the Rozansky-Witten models. And what I want to take here is the 3 category of topological defects in Rozansky-Witten models. That's my target category. So I have to tell you what this is. But the problem is that's very complicated. I mean, these categories were somehow, in a sense, written down by Kapustin Saulina, I think. Or maybe Rozansky-Kapustin also. But anyway, so these are very complicated things. And what we did to make this feasible, this project, to make this very explicit, is we didn't take somehow all Rozansky-Witten models, but we only took somehow affine Rozansky-Witten models. And these are Rozansky-Witten models where the target spaces are just T star of Cn. So we restrict on a very simple class of Rozansky-Witten models, namely the ones with these target space, which are called affine Rozansky-Witten models, because this is an affine space. Okay, so that's a hyperkähler manifold, and you can, quantize this and so on. So now what I want to do next is I want to tell you sort of, or at least give you a hint of what's the category, the 3 category of defects in Rozansky-Witten models of this type.
Yeah, so like the standard sigma model Lagrangian and this target space. That's what we're doing.
Yes. And you topologically twist, so that's a topological theory. Okay, so what are the objects? Well, the objects are just the affine, these were the quantum field theories which you are talking about. So these are just the affine Rozansky-Witten models. So you can identify the object with the target spaces. What we want to do is, we label them by lists of variables, like T star of Cn for us looks like this. It's x1 to xn, and the x1 to xn are just kind of the bulk fields of the theory, which somehow parameterize the C to the n. Okay, so these are the bulk fields. So I want to label these objects by the bulk fields. The one morphisms are now topological surface defects between 2 of those things. And these topological surface defects are described by something else, namely another list of variables A, which can have any length. So these A's are just other fields, if you like. Actually, they are fields which are localized on the surface defect, so additional fields, and some potential, which is a polynomial in these fields on the surface defects, and the bulk fields on the left and the right of the surface defect. Right? Maybe.
Both x and y have the same n?
No, they could, this could be a morphism between 2 completely different theories. So there could be T star of Cn and T star of Cm. Right? So they don't have the same number, and A also doesn't have the same number of entries. Okay, what are 2 morphisms? So maybe I'm not sure if I want to draw kind of a image like this. So we have T star of Cn, which is described, let's say, by x, and then we have T star of Cm, which is y, and then here I have other variables A, and this W of A, x, and y, some polynomial. Yes, these are fields which are local. They correspond to. I mean, this is math. You don't have to say anything about fields here to define this. But think of these as additional fields which are just localized on this two-dimensional defect. And these fields couple to the fields on the left and the right by means of this potential W. Okay, and this looks very much like a Landau-Ginzburg model, right? It's, you have a potential there, and if you think Lagrangian, that's basically a Landau-Ginzburg model, which oh, sorry, bar, it should be below, sorry. So that's kind of the. Okay, and the next step is, of course, to think about, one dimension higher. So what are the two morphisms? So there are no morphisms between these surface defects. And so physically, I think about this as line defects. It's a line defect between this surface defect and this surface defect. And I told you this looks like a Landau-Ginzburg model. And in Landau-Ginzburg model, one really knows how to describe line defects very well. And the line defects correspond to what is called matrix factorizations of actually the difference of these potentials. So what is this? This corresponds to a module of the polynomial rings in all these fields, which has a set Z2 grading. So x, that's the module, it's x0 plus x1. So 0 and 1 are denote the gradings. And on this, you have an odd endomorphism, which we call dx, and which has the property that it squares. So if you square this, then you get the difference of the superpotentials of the potentials here times the identity of x. Okay, so that's a matrix factorization. It sounds complicated, but if you work with it, it's kind of easy algebraic thing to work with. So these are line defects. Yes.
The field X, they are fields of the RW.
Yes, on one side of the defect, yeah.
But why not just specify how the domain will, for example, maps one both to each another? Why do we have to talk about fields?
Well, because there are more. You can do this. I mean, there are defects where just say, well, the fields on the side x and the fields on the side y are just glued, like x1 is equal to y1. But this is a very silly, simple defect. That would be the identity defect. You wouldn't see this, right? But they're more complicated. So you could think about more complicated things. But the way this works is that to generate the biggest class of these defects, you do this.
Oh, sorry. So should I maybe can I think of X as states of T star Cn on this codimension one?
X are the fields on the left.
The fields on the left.
Or at the right of the defects. These are the bulk fields. And W, this potential, somehow couples on this thing, on the surface fields with bulk fields on the left and the right. That's just, you write down sort of an action on the surface defect. So add an action there, which has this superpotential, has additional fields, and that's how to think about this. That's one way to think about it. All right, so, these are the line defects. So these are these things here. These correspond to matrix factorizations. And then, you have three morphisms, this three-dimensional TQFT, and the three morphisms, which correspond to point defects here, these three morphisms correspond to homomorphism of these things. They are module maps between x and y, phi here, which are even, so they map x0 to y0 and so on, and x1 to y1, and they have to commute with this d axis. So phi composed with the axis, dy composed with phi, and you mod out chain homotopes. I don't want to explain this in too much detail because it won't matter later. So anyway, but you can write this down, and one thing you should also do is think about what are the higher compositions, right, on this. So there's a one composition. So if you have two surface defects like this, and you push them together, then what do you get? right? And the answer is very simple. Namely, think about this physically. What you do is you squeeze in this model in the center. You squeeze them together. So these, fields in the middle, they're just promoted to fields on the new defect, right? Because, they don't have anywhere else to go. They're just in this plane now. And then you just add the respective potentials. So that's what this fusion is. So, list the defect fields. So A prime and A now live on the same defect. The Y's now also defect fields on this defect. And you add this potentials on both defects. So it's a very simple thing to do. So that's the one composition. Then the two composition is the following. So you start with a defect like this and two line defects. And these now correspond to matrix factorizations. And well, I just, I don't want to explain it in detail, but the point is that, the operation here is just the tensor product operation of matrix factorization. So you just tensor to matrix factorization and get a new one, and this works out. And the last composition is the three composition. So there you have 2 point defects, which correspond to homomorphisms of matrix factorization. And if you move close together, it's just the composition of these homomorphisms. So that's very simple. Okay. So now I have this target category, and what I want to do is I want to find the fully dualizable objects. Well, the objects already correspond to the quantum field theories I want to describe, so that's good. That's the right thing to do. So what we really have to do is find the dualizing data. Find duality data. That means adjunction maps for all objects in three category of defects in affine RW models. And once we have this, once if I take an object which corresponds to a three-dimensional Rozansky-Witten model, unextended, and I find all the duality data for this, so the dualities maps and then the higher duality maps and so on in all the three layers, then I have constructed my extended TQFT. So that's all I have to do. Well, that's kind of a big program, and you run into the following problem. No object is fully dualizable. Okay, this seems to be a setback, but of course, because this means that you can't really construct the extended theories, but this obstacle is kind of, in a sense, expected, because T star Cn is a non-compact target space. So this means, at least all the physicists know, is that the Hilbert spaces, therefore, of these theories are infinite dimensional. But in the category of Hilbert spaces, only the finite dimensional Hilbert spaces are dualizable. So it's not expected at all that that's possible to do. And the point, you could formulate it this differently. Three-dimensional Rozansky-Witten model isn't really well-defined 3D TQFT to start with, because you can't, evaluate correlation functions, for instance, on a torus, in a higher dimensional torus, because this would be a trace over such an infinite dimensional Hilbert space, and the answer would be there won't be any answer. So from this point of view, this is not a well-defined thing to look at, but still you can do something, namely. So one solution would be, well, just take a compact target space, and then you should be able to do it. But this is more complicated, so we decided not to do that. But instead, we truncate it this 3 category of defects to a 2 category, so the homotopy category. And what this is really is the following. So we don't want to go all the way up to 3 dimensions. We want to stop somehow in 2 dimensions. And so what we do here is, so we take as objects the affine RV models, RW models, as 1 morphisms. We take the surface defects we had before. And as 2 morphisms, we take the isomorphism classes of line defects. And then we stop. So we just do a two theory. So we don't want to go all the way up because we know there we run into infinite dimensions, and we don't want to deal with infinite dimensions. So we just stop before that. Which means that in the end, if we have constructed everything, we won't be able to evaluate our theory on 3-dimensional Bourdisms, but on everything below. So in particular, we can evaluate at 2-dimensional Bourdisms, and with this can at least calculate Hilbert spaces. Okay, so that's what we want to do. So now we want to take this category and now call this C. And now we want to find the duality data in C. In this truncated thing. And then we get a truncated TQFT, which now goes from board 210 into C. So you can only describe things up to dimension 2, but it's the price we pay for choosing something with a non-compact target space. Yes, so we get the infinite dimensional Hilbert spaces. We can do this because they are associated to surfaces, to 2-dimensional things, right? 2-dimensional things give you the Hilbert spaces. So we can calculate this. What we can't calculate is correlation function on higher dimensional things. Because there you would be, if you could do this, you could take a 3-dimensional, 2-dimensional manifold and then take it times as 1. And this would give you the trace over this associated vector space, which is infinite dimensional. So this doesn't make sense. We can't, compute this higher, but by this we at least can compute all the Hilbert spaces, which indeed are all infinite dimensional.
Can I ask a similar question, which is if one day we could find a way to do this by compactifying the target space,
yes,
would the results here tell you anything about those results?
Well, if you take non-compact target spaces, then you're, this category of topological defects, it's way more complicated. There are many more things in there. And so you would have to work in this category and find the respective duality maps and so on. If you do this, then you would get sort of, I believe, full dualizability of all the objects, and then you would be able to go to board 3210 and into this defect category, and then you can calculate everything.
So the C computed here would be the truncation of this really nice target.
No, not really, because here we only chose this, as objects, the affine RW models, and not all of them. So this is a small part of the whole story.
So correlation functions in the true theory.
Yes.
Would not necessarily be between states of these Hilbert spaces we're finding.
No. I mean, you have more, completely different Hilbert spaces there. Okay, so now in this sort of truncated setup, you can do everything. And I just want to flash this to tell you that it's extremely explicit. It's really something very easy you can give to an undergrad student to work out. So the objects here were the objects we started with corresponding to T star Cn, so just lists of the bulk fields. the dual of the list is the list itself. So, you know, duality is kind of simple. Then you have evaluation, co-evaluation, and 1. And they all look like the identity surface defect. And, you know, this has just as many sort of extra variables as there are variables in the bulk. And the potential looks like this. So this is a Lagrange multiplier, and this goes in the direction of the question you asked. It's a Lagrange multiplier which sets xi to yi at the boundary. So that's the identity defect. And you know, all these maps basically arise from this identity defect. So it's very simple, right? If you think about it, the idea is extremely simple. And then you can show, if you take this and you just work out these one composition of these things, that they satisfy the Zorro identity. So they are really dualities for these things, for this dual, so really adjunction data for this duality. And then you have two adjunctions, you know, which correspond to surfaces like this, right? We know, you know, that this is the evaluation of the evaluation, and you know, these are just some very simple tensor products of matrix factorizations, and they are extremely simple matrix factorizations. I don't want to explain this because I'm anyway way out of time, I guess. But it's very explicit. It's not complicated at all. Very explicit, and one can explicitly compute that these things satisfy the Zorro identities as well. So then, if we have this, now we have all the adjunction data, right? We know, you know, what's the adjunction data of X. So like this and this and this and this. So we can calculate everything we want to calculate. So for instance, let's do a correlation function via gluing. So let's take a correlation function of a genus G surface, closed surface. And this we somehow cut in sort of G parts like this and cap and cap like this. Then, you know, if I want to calculate the correlation function, I have to calculate the correlation function of this. And then I have to take the correlation function of this and raise it to the power of G and then compose it with the correlation function of this. Okay, simple. But now, this here is the evaluation of the co-evaluation, which we calculated before. This is the co-evaluation of the evaluation of my model, which I also know. And this part I can get out of the identity of the co-evaluation of the co-evaluation, the evaluation of the evaluation, and the identity on the evaluation, right? So I know all these things because I know the complete duality data of this object, so I can really calculate everything. And if I put everything together, I get this kind of result. And that is supposed to be the Hilbert space associated to this surface here. Okay, and indeed, this is isomorphic to the result one gets by sort of standard quantization methods, which were put forward by Rozansky and Witten a long time ago. So one can really sort of calculate the things one already knows. But the point is that we can now do more. We can go to non-closed surfaces. So for instance, we can you know, also evaluate a T on, for instance, the pair of pants. And, you know, the cap and the handle. So you can evaluate all these things, which people hadn't done before. And in this way, we can actually get a categorification of Frobenius algebras. And all these things are associated to some defects. So this, for instance, is a junction defect. So we have 3 surface defects like this, which meet in a junction. And this thing here, so the correlation function of this here, so T of this, corresponds to a sort of junction line operator in where these are all the identity defects, surface defects in this theory. So very specific. And yeah, for instance, the cup corresponds to a particular line operator and so on. So in this way, one finds sort of a categorification of a Frobenius algebra as well. So that's somehow part of the story. But there's another part which since we constructed this thing out of defects, we can now also incorporate defects. Now, up to now, I've told you how to calculate just normal correlation functions. But since this whole story is made up of defects, one can now find correlation functions with defect networks on space-time in a very simple way, or a very straightforward way. So now we, instead of just a surface like this, we could decorate the surface by kind of defects, where you have to decorate these defects by fully dualizable morphisms. So d-dimensional, d-1 dimensional defects, for instance, are have to be labeled by 1 morphisms, which are fully dualizable, and so on. And now, if you do this, you can just turn the crank as before, right? What you now need is that so need that objects are fully dualizable, but also the defects. So all defects are fully dualizable. And then with the duality data of all of this, if you know the duality data of all of this, you can sort of calculate all the correlation functions of all possible Bordisms with all possible sort of forms of defect inside by just using the same pictures. You cut everything into these, junction maps basically, and then have to put it together. So, for instance, just as an example, I take the torus with a defect going around here. Let's call this defect D. And this thing can be calculated. This corresponds, what does it correspond to? This corresponds to the Hilbert space of a theory where you take your space-time to be this torus times time or something, and on d times time you wrap a surface defect. So this defect here is sort of labeled by a surface defect, and that calculates the Hilbert space of this thing. And now this can be very easily described as the evaluation of xd composed with a co-evaluation of xd, which is also the quantum dimension of xd. And xd here, xd is just t of the circle with d inserted. Okay, so this might seem somehow complicated, but it's very simple because all these things we know already. We can, we have very explicit formulas for these, and formulas which an undergraduate can sort of learn to deal with. It's very, very simple math actually to do this. Okay, of course I don't want to bore you with any more calculations. Just give you somehow summary. And the summary is this. So what we did is we started with a 3 category of defects in Rozansky-Witten models. We truncated this category to this homotopy category, where we just stopped at the line defects and took isomorphism classes of them. So that's this truncation, which was necessary because the models, these affine RW models, have infinite dimensional Hilbert spaces. And then we find that C is a pivotal symmetric monoidal 2 category. That means in particular that every object is fully dualizable, every one morphism is dualizable, And there are some coherence conditions which I haven't mentioned before. And in this way, we can obtain so-called truncated affine Rozansky-Witten model as extended defect TQFTs. So we can incorporate defects as well. And all the correlation functions can be obtained by gluing simple pieces. And by doing this, we find sort of interesting structures, like, for instance, this categorification of the Frobenius algebra structure and so on. Because this truncated thing is a two-dimensional TQFT, which has values not in vect, but in some more complicated category. So that's basically the end of my talk. As I said, there are many technical details I swept under the rug. So if you're interested to hear more about this, I'm happy to tell you. But I really want to stress that this is very explicit, really. I mean, the formulas which one uses to calculate is down to earth, and we can really calculate these things explicitly. You can probably put it on a computer also, and it's not complicated math at all. And of course, we have done this in this simple example, but of course it would be really nice to do it in more complicated examples, for instance, where the target spaces are non-compact. But the problem there is that the category of defect is more complicated. So at least for me, it's not so easily accessible. But there might be mathematicians who are able to do this, and would be very nice to go all the way and don't only have a truncated version, but somehow the full extended theory of this. And also there are other directions which one can go. So one can, for instance, instead of taking Rozansky-Witten models, take gauge Rozansky-Witten models and so on. And that's, for instance, a project we are looking at right now, and it also seems to work out very well. And yeah, so that's what I wanted to say. Thank you. Yes. Yes. We go to the homotopy category and forget everything in dimension higher than 2. That's kind of the truncation. Because, this things in higher dimension, we cannot calculate. There's just no way to calculate it because this doesn't exist, right? You can't, at least not all correlation function on higher dimensional spacetimes can be calculated because, it could be the trace of something infinite dimensional. So there's no way to do this formally in this kind of setup. There might be a way, to introduce some gadgets to do this, to make this a little bit finite dimensional, like introducing formal variables or something like this, and taking, instead of the dimension, some graded dimension or something. But, I haven't really, I cannot say more to this. I just don't know. Yes.
Just allowing certain organisms like will be able to take traces.
Yes.
Stop being a problem. Do you know if you expect that things will be really joinable in that sense?
You mean like if you don't sort of allow all pieces, but only the ones which are sort of finite, or?
Yeah, so you can unwrap what you would need for a functor out of 4.
Yes. But the problem with this is that, these pieces, I mean, you have to, these adjunction pieces, they contain pieces which are not well defined or cannot be well defined because the trace is built up of 2 of these pieces. So the problem is that the adjunction data, the full adjunction data isn't there. And, it's hard, if you want to prove that something is an adjunction, you need all the adjunction data because you need all these Zorro moves, right? And so there's just no way. So this is not, the infinite dimensional vector spaces are just not dualizable. So there are no dualization, the junction maps in this case, which you can use to build up everything. So that's the bug in this. So this thing you can't use for calculating even, the TQFT on something 3-dimensional, which is finite. That's the problem. I agree with it because, in order to get this, you need all the parts, and some of the parts are not well defined in the case of the non-compact target space. I think that's probably the answer to your question. Or, yeah.
Could you go back to the slide where you write down
This one?
So it's just the two sphere, then it's polynomial algebra, and G is 0. The answer is infinite dimensional.
Yeah, that's just a polynomial ring in these variables x and a. So it's just a polynomial ring, obviously infinite dimensional. And that's, of course, physically, that's the answer you would sort of expect. That's just, the space is isomorphic to the fields which are there on this thing, and they are just those things.
So I appreciate that these RW models are really physically interesting, and that's why you want to build a target.
Yes.
But if finiteness and getting generalizability is the issue, can you just start with some modular tensor category in 3D and find its two category of defects, and then use that as your target? Is that okay? Maybe some.
Yes, of course you could. That's a very. I mean, of course you can start on this in this way. If you have a nice defect category and you know that things are fully dualizable, you can construct extended TQFTs with this. I would know what, you have to find out what is the TQFT you are extending. I don't know. It depends on the choice of your category.
I see. So like, is the, I guess, philosophical problem with extended TQFTs often finding the target? I imagine that's quite hard because we know the border.
Yes, of course, but because you don't know many, higher categories and the adjunction data and, these, all the axioms, and so just to check that this is a higher category is always very bad. I mean, very difficult to do.
So if the target is the category of defects for a 3D TQFT,
yes,
which comes from like a modular tensor category,
yes,
is that always dualizable?
I expect it, but I don't know. So maybe.
If it was, then we're happy.
Exactly, because then we can extend it. But there might be TQFTs which you cannot extend. I don't know. And then, of course, it doesn't work. But if they are extendable, then they should be fully dualizable. But, I mean, it's a very high, these things are very hard. And I'm also not a mathematician, really. I'm a physicist. I'm really interested in examples. And, and here, what we did was basically, show in this simple example how out of very simple pieces to do it, and also, give an idea how the adjunction data would look like for more complicated examples, because the adjunction data basically corresponds to what in physics one calls the folding trick, and it's basically also always variants of the identity defects which are there. And here we really, we only have to turn the crank. It's very explicit and can calculate everything. In more complicated examples, I would know how to do this. But if anyone knows, that would be a very interesting thing to do, especially for the compact cases.
Do you think the same logic would apply for maybe Chern-Simons theories? That's another class.
I guess it should work for more or less. If you know the defect categories, you should probably. I don't know.
Okay.
Yes.
So you didn't say anything about.
Yes. Yeah, that's one of the details I didn't.
Are these oriented theories?
These are, well, I didn't mention certain things here. If you want to do this oriented, you have to specify. First you do this framed. But then you introduce some kind of Serre isomorphism or automorphisms into this. I mean, there's a certain level of complication which is added to everything, which I swept under the rug.
I understand the general statement.
Yes.
It's this particular example.
Yeah, we did it for oriented. Yeah, we did it for oriented, yes.
And then, so presumably one has an action mapping paths from these vector spaces.
Yes.
With torus, is that something that you've calculated?
Yeah, it's a long time ago. We probably looked at that, yes. But I'm not sure. I have to look this up. But in principle, yes. In principle, it should be one should be able to do these things. No. But I mean, these are all, it's easy to, I mean, it's not difficult to do. One can just, work this out. This example is in a sense, it's very nice because it's very, very easy. And you can do all these complicated stuff and just try it out and, very explicitly get results. And that's the beauty of it. But we just, did the oriented case because this is the sort of most natural things occurring to us at least. But you could do everything else if you like.
So related to what Kevin said, if you have like a mapping cylinder, do we know how to decompose it into generators? Do we know how to do that?
Because that's a three-dimensional thing, a mapping cylinder. So we only know 2D stuff, right? I mean, we can't do the 3D pieces.
Yeah, I see.
So. But as I said, if anyone would be able to do it for even simple hyperkähler manifolds which are compact, like TPN or something, T star PN, then this would be very nice. But the defect categories even for T star CPN is kind of much more complicated and less accessible to me. But I'm sure there are mathematicians for whom this is completely different, and they would be able to do this in like this. That's right. Yes. I mean, in their paper, they are very, they are not very detailed in a sense. Their proposal of this category is not very detailed, and you have to check all these, axioms basically and construct all the respective maps to deal with this. And for compact things, I don't think anyone has done this, but at least for simple ones like T star CPN, this should be possible.
We should stop there.